Now let's prove the chain rule. It's actually really rather complicated to prove, so we're going to do it for one special case, which then will be extended in your text if you want to see the whole proof. But for this case, we'll just make the assumption that g of a is not the same as g of x. So we need to prove the chain rule, and that is that when h of x is equal to f composite g of x, then h prime of x will be equal to the derivative of f, that would be the outer function, with respect to the inner function g of x, times g prime, the derivative of g with respect to x. Okay, we'll make the following assumption. Assume that f and g are differentiable functions. And one more assumption, assume that h of x is the composite function f of g of x. Then we're going to apply the limit definition for h prime of a, where a is just some dummy variable. The limit as x approaches a of h of x over h of a equals x minus a. That's one of the definitions we've seen. But now we'll replace h with what it's defined to be equal to in this problem, f of g of x. So we get this statement for the limit. Next, we're going to multiply by some strange form of 1. The function is now f of g of x minus f of g of a over x minus a. I had to make a little correction up on the step above. Now we're going to multiply this by g of x minus g of a over itself. We're trying to set this thing up. That's why we chose to use this particular form of 1. It's just 1. Okay, so we're going to multiply, and we're going to switch out the bottom functions because we're multiplying. There's a commutative property of multiplication. So the g of x minus g of a comes to the left, and then the other factor, x minus a, in the denominator comes to the right. And that is just an application of the commutative property of multiplication. The denominator of one was multiplying the denominator of the other, so we could exchange them, we could move them around. Okay, now we're going to distribute the limit across the multiplication. So we've got the limit as x approaches a of the first factor, which is f of g of x minus f of g of a over g of x minus g of a. And then multiply that entire limit by the limit of the second factor as x approaches a, g of x minus g of a over x minus a. Now I'm going to do a change of variables in one of the limits, so listen up to this. Oh, I made a mistake over there. I went back and crossed it out. There's no such thing as erasing in these videos. You just cross them out. So I want to change the limit. So now we're going to assume that we did assume at the beginning that g of x was differentiable. All right. In other words, a derivative existed. Thus, we know that g of x is continuous because differentiable implies continuous. So what's the definition of g of x being continuous? It means the limit as x approaches a of g of x is the same as g of a. But that implies that g of x is approaching the value g of a as x approaches a. That's what we just said on the line above. So we may we're going to rewrite our statement above as h prime of a, that's what it was, is equal to the limit not as x approaches a, but we'll change it to as g of x approaches g of a, because we just demonstrated above in the brackets that that indeed is true when x approaches a. And then we go ahead and write the quotient function f of g of x minus f of g of a over g of x minus g of a, and then bring down the limit as x approaches a as normal of g of x minus g of a over x minus a. We just changed what the limit was approaching in the first factor. Okay, now these should look familiar. The one on the left is actually the definition of f prime of g of x, and the one on the right is actually the definition of g prime of a. And by the way, we could not have even said that that's what these two limits were equal to if we didn't already know at the very beginning in our assumption that f and g were differentiable. Thus, we have shown that h prime of a is equal to f prime of g of a times g prime of a. But a was just the dummy variable. We didn't consider it a constant here. We just considered it some variable. And so we can call it any variable. And in this case, we're going to say let a become x so that we can rewrite this statement as h prime of x equals f prime of g of x times g prime of x. There should be a prime there. And that is exactly what we are trying to prove. So we have finished in our proof of the chain rule in this special case.